So we were discussing exterior product. So last time we were started discussing exterior product. It is a vector space. Over a field A, let's say. So the exterior product with B is a subspace of the tensor product, and it's product of things like this in K and let's say W K minus W K times D K. Finite summations like this. So D K and W K are elements of D. This is certainly is a subset of V tensor D. And in short, we write for this instead of this, we write V H W, right? So this thing is V K H W K. So they are just special tensor products. Similarly, what about this digit? So they are elements of this family. Here, of course, n is an integer, positive integer. You may have just one term, two terms, three terms, as many terms as you want. And here, n is an integer, positive integer. So, instead of this, you may consider objects like this. VK, let's say UK, WK. Again, UK, WK, or UK, WK are element B. And is an integer. So it's an integer. And what is this expression? So again, it's the before V times V, and here this gadget, right? So V U with W. This is just alternating sum of tensors, right? So V times V times W, and then you just keep changing, right? You let's say change this to, and then you change this to U times W times V, and then you change this to W times U times V, and then I can do what? V'yi başarabiliriz. Bir başlıyoruz zaten ama şu da olabilir. Bir tanesi W tanesi U, değil mi? Şimdi okay, so this will be minus because this is plus, this is minus, and then W cancel, V cancel, U. Since it's minus, this will be plus. You just take all possible triple tensor products, but each time you have a sign this. So DUW. This has positive sign, and all the others will depend how many transpositions you make. This is one transposition, therefore this minus. This is obtained from this one via two transpositions. You interchange this two, and then you interchange this two, you obtain this. So accordingly, you get all things like this, and this thing is just nothing but finite sums of objects like this. Okay. Now, we have a notation we can ya da şöyle diyeyim. Bunları böyle tarif edebilirim. So, since tensor product is already defined, these are defined. But we may define wedge product of vectors in an alternative way. Alternatively, we may define wedge product or exterior product, wedge product or exterior product as follows. So we may consider okay, so G tensor E is the abstract, is the vector space of formal objects. Şöyle daha birden örnek kadar we can answer not answer wedge product W K where this object satisfy the following properties. Nedir onlar? Birincisi şu, the wedge product W is the same as this one. Yani burada this time forget all this. I just define this vector space from scratch as follows. So this is just the set of such objects where these are some vectors from V, and this symbol satisfies this property. So whenever you have this, if you interchange two components, you pick up a minus sign. And the second one is this. If you have sum of two vectors here, the wedge product with this guy will be regarded the same as this one. Okay? And if you have something like this, then this will be regarded as this one. Okay? So you may forget all this, tensor product definition, and instead consider this thing as the vector space of such formal sums, where these gadgets are just objects from our vector space, and I have this symbol in between them. And whenever I have this gadget, I will regard this guy is the same as this guy. So if I change two components, I will have a minus sign here. And we have this. Of course, using this, you have the same property for the other one. Namely, note that one and two, but you see, if I have B batch W1 W2, what will be this digit? Well, from 1, this is the same thing as this one. And then from 2, this product is just W1 with B plus W2 with B. So this is minus W1 with B minus W2 with B. But again, using the first one, this is the same as B with W1 and B with W2. So if I just assume this 2, I get this one for free. Similarly, okay, V H lambda W is 1. Well, this is just minus lambda H this, but we know that this lambda goes out because I have this, so this lambda goes out. So this is just minus lambda WHB. But then, if I just replace this 2, I pick up a minus sign. Therefore, we get this. So what we obtain is that if I have DH lambda W, I can take this lambda outside. Okay. So you may use either definition. Either this definition that this objects the tensor W is this tensor. Similarly, this tensor is just this tensor. Or you may forget this. You may forget this and say that this vector space is defined to be the vector space of finite sums of like things, objects like this. But this thing is again a formal object obeying these 2 rules. Okay, whenever I have this, it is equal to this one, and I have this one. And this 2 gives me also these conditions. Again, from this, you see what? See the following. What is VHV? Now, if I interchange this 2, I pick up a minus sign. Therefore, we get 2 times VHV is 0. And from this, we get VHV is 0. If 2 is not 0, we check. Yani 2'nin 0 olduğu field'lar var değil mi? F2'de 2 0. Eğer 2 0 değilse o zaman bu 0 olacak. 0'sa bir şey diyemezsiniz. Ama 2 0'sa zaten 1 ile eksi 1 aynı şey. Right? If şöyle yazayım. 2 is equal to 0. Then 1 plus 1 is equal to 0. This implies that minus 1 is the same as plus 1. And hence d with d, which is 1 times d with d, but 1 and minus 1 are the same, so this is minus 1 times d with d. Yani gene aynı şey. Onlar birbirine eşit olacak. D ve H'nin 0 olduğunu söylemek istiyordum ama o 0 olacak mı? V ve H şu yüzden de 0 olacak. Dur. Niye 0? Belki şöyle neyse tamam. İlk tanımdan sıfır da niye sıfır? V dash D is from the first definition. This is V dash D minus V dash D. Therefore, this is from the first definition. But from the axiomatic definition, I don't see why it is zero. Delta'nın lambda'yı sıfır olarak neyse. Karakteristik 2 her zaman baş belasıdır zaten. Hani ama diğer yandan çok da kullanılıyor. Okey.
Beş olması içindeki bütün elemanların 5 toplam.
Neyin sıfır üst olması?
Evet, B ve C'nin olması orada gösterdik yani tensor product'lar onların tam. Onlar hepsi ayrı ayrı mı? Yoksa
Yok.
samların
yani B ve C şuna eşit. Eğer ilk tanımı kullanırsak B ve C is justice and it is zero. Okay.
Şu birde var ya I5W işte XW.
Evet.
Onu kullanarak olmaz mı? Orada I5 geçti. Eksi I5 karşıya.
Tamam öyle yaptım. İşte 2 çarpı bu 0 ama buradan buraya nasıl geliyorsun? Eğer 2 0 değilse bu doğru. 2 0'sa burada kalırsın. Değil mi? 2 0 değilse if 2 is not 0 I can divide by 2 and obtain this. But if 2 is 0 you cannot do that. However, I mean the actual definition of external product is there and from this we already know that it is 0. All right. But, you know, this way of thinking is practical because, you know, even for this triple exterior product, we have 6 terms. For 4, I mean, exterior product of 4 vectors will have 24 terms. Right? It is n factorial many terms, so it is not practical to use that gadget. Okay, however, you know, in general, we can do this. We have this definition. The exterior product of K couples of B denoted by this notation is defined as the subspace of totally anti-symmetric tensors within B tensor, K copies. Bunu da şöyle gösteriyoruz bazen. This is also denoted like this. Okay. Genelde şöyle de gösterilebilir herhalde. Yani B'nin kendisiyle K kere tensor produktı gibi. Burada totally anti-symmetric tensors dediğimiz şey nedir? Totally anti-symmetric tensors. So this gadget will be consist of things like this: V1, Vh, Vk, okay, the auxiliary V. Totally anti-symmetric means anti-symmetric means what? Whenever you have, let's say, something like this, Vi, and then I have Vj, and then let's say Vk. This is just the negative of what? V1 up to Vi, but let me just interchange this two, okay? Vj, Vi, and then Vk. So whenever I interchange two of them, I pick up a minus sign, okay? Well, this thing, V1, V2, Vk will be then what? You know, if I use the similar representation, so we will have the following. We will have -1 to the power. Here, this kind of notation. The sigma 1 cancel the sigma k. This is in K. Sk is just the set of all permutations of this set 1 of K. Yani birden K'ya kadar bütün permutationların şeyi. And what is this? This is the parity of sigma, meaning that the parity of the number of necessary permutation transpositions which transform sigma to the identity permutation. So what I mean this, if let's say sigma is in suppose k equals 5, okay. So we consider objects like this V1, V2, V5. And this is what? This is just summations over S5. All permutations in S5 -1 to the power this. And then I have V sigma 1 cancel up to V sigma 5. So each sigma is a permutation. So this indices goes from 1 to 5, but in any order. You may have 1, 2, 3, 4, 5, or 1, 3, 4, 2, 5, or 5, 4, 3, 2, 1. What about this thing? This is the so this gadget is the number of permutation transpositions which brings this permutation to the identity. For example, suppose this is the permutation given like this: 1, 2, 3, and then 4, 5. Right? It's an element of S5. What is this? So bunu identity'ye dönüştürmek için ne yapmam lazım?
İkili elemanlara bölmüyorum.
Yani kaç tane transposition var, değil mi? Bu nedir? Bu 1, 3, 2 mi?
Evet.
1, 2. Bu da 4, 5. 3 tane var, değil mi? So this is just 3, but I look at in mode 2, so it is just one mode 2. Therefore, it's the sign will be negative. Okay, the sign will be negative.
Bir şeye bakarak da söyleyebiliriz değil mi o zaman onu? Yani kaç tane transposition varsa oradan paritesine bakın.
Evet. Evet. Yani evet, bunu belki hani number of transposition olarak yazdım. You write sigma as a product of transpositions, and then you count how many of them. That number is always even or is always odd. So depending on whether it is even or odd, this thing will be 1 or -1. So just the same idea. So here we define extended product of k copies of V as the vector space of tensor products in this vector space. What kind of tensors? They are totally anti-symmetric. What does that means? Totally anti-symmetric. So whenever you have a tensor product, when you interchange these two, you pick up a minus sign. Okay, and that actually corresponds to the following. An element of this type is just this tensor product. Some of this tensor products. Here, summation is over all permutations of the symmetric group on k letters, and for each sigma here, we have this sign, and that is nothing but the parent of the permutation. Namely, you write this permutation as a product of transpositions, and then you check whether it is even or odd. Depending on whether it is even or odd, this is just plus or minus. Okay. Peki. Let's do some examples. Let's say in R2, so my vector space is R3, and we take 3 vectors. In this one, 0, 1 over 2, minus 1 over 2, B is 2 minus 2, 0, and C is minus 2, 5, and 3. We would like to compute A weight, B weight. That is this figure. But to make life easy, let's use this standard basic elements. And then this becomes what? This is just 1 over 2 times E2 plus, no, minus 1 over 2 times E3. This is just 2 times E1 minus 2 times E2, and this is minus 2 times E1 plus 5 times E2 and 3 times E3. So, this gadget is then equal to what? This is just 1 over 2 times E2 minus 1 over 2 times E3 minus 2 times E1 minus 2 times E2, which minus 2 times E1 plus 5 times E2 and plus 3 times E3. Okay, now what will be the result? Okay, now wedge products are linear in each component and anti-symmetric. Linear in each component means what? So here I have sum of two vectors, wedge product with something. I can write this as 1 over 2 times E2 wedge, this given 2E1 minus 2E2 wedge minus 2E1 plus 5E2 plus 3E3 minus 1 over 2 times E3 and the same thing. 2E1 minus 2E2 minus 2E1 plus 5E2 plus 3E3. And then I can do the following. You see, I can open now with respect to this one, but you see, if I open this one, E2 wedge E2 gives me already 0. So the only non-zero term will come from this one. So the first one, for the first one, I can write the following. E2 wedge 2E1 wedge whatever left here. And what about this one?
Minus.
Efendim? Evet. E2 için yapacağız. Orada şey var. Evet. Orada onu direkt yapayım. Eksi 1/2. Çarpımda ne olacak bu? 2 times E3 E1 minus 2 times E3 E2 wedge product minus 2E1 plus 5E2 plus 3E3. Okay. Okay. So we make this example in R3. I have these three vectors written in this basis as this one, and I want to compute this product. We write it like this. I open with respect to the first element of the tensor product because this is the sum of two elements, so I can write it like this: 1 over 2 times E2 wedge this minus 1 over 2 times E3 wedge this guy. Hangisini? here, this is just 0, so I have only this term, with this term, minus this guy, with this one. So if I wedge this 2, I will take wedge product of this 2. I get this one, E3 to E1, and then E3 wedge minus 2 E2, which is equal to. Okay. So A wedge, B wedge, C is just one. Now let's look at this one. If I take wedge product of onu yapayım oraya hesabı da ondan sonra. Yok pardon. Okay. I have E1, E2 here. If I take wedge product of this with this one, I will have E1 and E1, and it will give me 0. If I take wedge product with this one, I will have E2, E2, again it will be 0. So this will be the only non-zero term. So we have what? 1/2 times, 1/2 times E2, wedge 2 E1, wedge 3 E3, minus 1/2 times. What about this? I have this gadget. When you take wedge product with this one, it will give me 0 because I have E1 here. If I take wedge product with this one, this is E3, again it will give me 0. So this won't give me anything. The only non-zero term will come from this one. So we have what? Minus 1/2 times, minus 1/2 times, 2 E3 wedge E1, wedge 5 E2, 5 E2. But I have also this term, so minus 1/2 times, minus 2 times E3, wedge E2, and then wedge product of this with this guy. Well, I have E2 and E3. Wedge product with this one will give me 0. It will again be 0 if I take wedge product with this one, because I have E3 and E3 here. So the only non-zero term will be from this one. So okay, so I have that minus 2 here. So we have what? All this constant goes up, out, and I have 2, 3, 6 divided by 2. It is just 3. And then I have E2, E1, E3. Burada ne olacak? Eksi 1, eksi 5 tane E3 ve E1 ve E2. And again, minus 2 it would be plus 2. Bir minus 2 daha var. Yine minus 2 olacak. E3, wedge, E2, wedge, E1. But you see, this is the same thing as bunu ben E1, E2 diye yazarım. Right? So if I write minus 3, this will be E1, wedge, E2, wedge, E3. What about this one? This should jump twice. İlk önce buraya gelecek, sonra buraya gelecek. So you need 2 transpositions. Therefore, still minus 5. What about this one? Okay. I have to make this transposition, and then another transposition, and then another transposition. 3 tane gerekecek, değil mi? Ha, yerde bir tane. Şu ikisini yer değiştirelim, olur biter. Tamam. Dolayısıyla da artı 2 olacak. Bunu yapacağız. So what is the result? Then minus 6 times E1 with E2 with E2. Tabii biraz daha farklı ama yardım eder mi? Neyse. You understand what's going on? Şimdi şöyle bir soru var. Şöyle. Space wedge product or base and wedge product of this different from this. Yani ne demek istiyoruz? We may take dual of B and take its nth exterior power, or I can take nth exterior power of B. It's a vector space, and then take its dual. Are they different objects? Okay. But of course, here I should define, I have this vector space, and then I have its dual. So I should tell you how the dual elements eats these guys, and for that we need a definition. So answer. Okay, now we know that if A star, B star is a B star, and we are vectors, then we define A star cancel B star on U cancel B. Bunu nasıl tarif etmiştik? Herkes kendi sırasındakini yiyecek. Bu ilki, o zaman o bunu yiyecek. Yani A star U and B star B, and you multiply the numbers. Okay, now if I just use this definition for the wedge, let's see what we get.
Bu tensör değil mi?
Efendim?
Bu tensör değil mi? Bu şey olarak düşünüyorlar. Öyle
Nasıl yazmıştık?
Then
we define it. Şimdi bu tanımı kullanırsak, if we use this definition, then you would have, let's see, A star dash B star, and suppose we would like to know its action on this. Well, what is this? Is a tensor. This is just a tensor. A star, B star minus B star, A star. And this will act on U tensor B minus B tensor B. So we have 4 terms, right? This one will eat this one, and again the same. So if this guy eats this one, it will give me A star U, B star B, and then it will eat this guy, and it will give me what? A star B, B star U, and then this guy will eat this one. It will give me B star U, A star B, minus plus B star B, A star U. So you get the same thing but twice. So this is just 2 times A star U, B star B, minus A star B, B star U, right? We get 2 times this. It is kind of, strange. You don't want something like this. You multiply 2 quantities like this, and then you suddenly have an extra 2 here. But, if you define this like this, this is the result. So what we do, and actually, if you use triple ones, things get even worse. Okay, I'll do it in the next hour. You will see that if you have triple wedge products, then you will get this time how many terms? 3 terms here, 3 terms here. No, not 3 terms. Evet, each one will have 6 terms. So yeah, you get
Altı kere tekrarlanırsa da 6 parça yapacağız.
6 olacak sanırım. So this is 2 factorial. The next one will have 3 factorial. Okay, let's do it in the second hour.